On June 19th, 2020, at a distance of 124.2 astronomical units from the Sun, an instrument on Voyager 2 built more than 4 decades earlier picked up something specific enough to write down as an exact number, a frequency of 3.11 kilohertz, arriving from the interstellar plasma surrounding the spacecraft. Picture that reading the way it actually appeared on a researcher's screen back on Earth. Not a dramatic waveform or a flashing alert, but a single, narrow spike sitting quietly in one specific channel of a frequency chart. Easy to miss entirely, unless someone happened to be looking at exactly the right slice of data, at exactly the right moment. It wasn't the first time. A similar signal had shown up the year before, not long after the spacecraft first crossed into interstellar space. Before addressing what that frequency actually tells scientists, it's worth being direct about what it isn't. It's not a transmission, it's not a message, and nobody studying the data believes it originates from anything resembling intelligence. What NASA and a team of researchers at the University of Iowa actually confirmed is something quieter and more specific. Proof that Voyager 2 is picking up a real physical frequency generated by the electrons in the interstellar medium itself. A measurable signature of the exact density of space at the spacecraft's current location, arriving from a region no human-made object had ever sampled before either Voyager spacecraft got there. To understand why a specific number like 3.11 kilohertz matters, you first need to understand what Voyager 2 actually is and where this frequency is coming from. Launched in August of 1977 and just weeks before its twin Voyager 1, Voyager 2 spent its first 12 years completing the only spacecraft flyby in history of all 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, before continuing outward on a trajectory that would eventually carry it past the edge of the Sun's influence entirely, arcing downward out of the plane the planets orbit in on a path no other mission has ever repeated. On November 5th, 2018, Voyager 2 crossed the Heliopause, the boundary where the Sun's own bubble of solar wind finally gives way to true interstellar space, becoming only the second human-made object, after its twin Voyager 1, to leave the solar system. The instrument responsible for detecting that 3.11 kilohertz frequency is Voyager 2's plasma wave science instrument, built at the University of Iowa and led for decades by physicist Don Gurnett, using a pair of long antennas extending outward from the spacecraft like thin metal whiskers to listen for electromagnetic oscillations in the surrounding plasma. Hardware originally designed to study the environment around the giant planets. Voyager flew past, decades earlier, repurposed by simple physics into a tool for studying something its own builders never specifically planned for it to measure. Here's the physics behind why that frequency carries real, usable scientific information, rather than being some kind of arbitrary background noise. Interstellar space isn't a true, perfect vacuum. It's filled with an extremely thin cloud of ionized gas, plasma, made of free electrons and charged particles drifting at incredibly low densities, often just a tiny fraction of a single particle in every cubic centimeter of space. When something disturbs that plasma, a shockwave from a distant stellar event, or in this case a burst of activity traced back to our own sun and traveling outward for months before finally arriving, the electrons inside it begin to oscillate, vibrating it at a specific natural frequency that depends directly on exactly how densely packed those electrons are in that particular patch of space, the same basic principle that determines the pitch of a plucked guitar string based on its tension and length. Denser plasma produces a higher oscillation frequency. Thinner plasma produces a lower one. That relationship gives scientists a direct, reliable way to calculate the density of the interstellar medium surrounding the spacecraft using nothing but the specific pitch of the oscillation its instruments manage to catch, translating a faint radio signal into an actual usable measurement of how crowded a specific patch of the galaxy really is. Voyager 2's confirmation didn't happen in isolation. In November of 2019, a coordinated set of 5 separate research papers, all analyzing different aspects of the same historic crossing, was published together in the journal Nature Astronomy. The paper focused specifically on the plasma wave data, led by the University of Iowa team, confirmed Voyager 2's passage into interstellar space by identifying a definitive, sharp jump in plasma density right around the crossing point, the marked transition from the hot, comparatively sparse plasma inside the solar wind to the noticeably denser, cooler plasma that defines true interstellar space. Don Gurnett, the study's corresponding author, summarized what that jump meant for one of the field's older, long-held assumptions. The historical idea that the solar wind simply fades away gradually the farther you travel into interstellar space, he explained, turned out to simply not be true. Instead, the transition showed up as a genuine, measurable boundary, not a slow, indistinct fade. That first confirmed density jump was itself an echo of something Voyager 1 had already shown scientists 6 years earlier. And when Voyager 1 crossed the Heliopause back in August of 2012, its own plasma wave instrument eventually detected locally generated electron plasma oscillations at a frequency of about 2.6 kilohertz, first appearing in October and November of 2012, and again in April and May of 2013, evidence that the spacecraft had genuinely entered the denser plasma of interstellar space. Voyager 2's 3.11 kilohertz reading, appearing years later at a different location along the heliosphere's boundary, showed a noticeably higher frequency than what its twin had originally measured, translating directly into a higher electron density at Voyager 2's specific position in the surrounding interstellar medium. The difference between the two readings is exactly what makes having two independent spacecraft, rather than just one, so valuable for actually understanding what's happening at the edge of the solar system. William Kurth, a co-investigator on the plasma wave instrument who worked alongside Gurnett for decades, offered a vivid way to picture the challenge scientists face when trying to build a complete picture of the boundary from just two data points. He compared it to two people examining an elephant with a microscope, each one arriving at a completely different measurement depending on exactly which part of the animal they happened to be looking at. One perhaps finding the rough, wrinkled texture of an ear, the other the smooth curve of a tusk, with no way to know what's actually happening in the vast space between their two narrow observations, or what the elephant as a whole actually looks like, based purely on those two disconnected close-up glimpses. Voyager's models, he explained, work by taking the specific information gathered at those two individual points and combining it with everything learned throughout both spacecraft's long flights, trying to assemble a single, coherent, a global picture of the heliosphere's true structure out of what amounts to two isolated close-up glimpses, filling in everything in between with physics-based extrapolation rather than direct measurement. The 2019 confirmation also settled a genuine point of scientific uncertainty that had existed before Voyager 2 actually completed its own crossing. Based on pre-crossing models of the heliosphere's shape, some researchers had expected Voyager 2 might actually reach the Heliopause before its twin did, since its trajectory carried it toward a different section of the boundary. That prediction didn't hold up. Voyager 1 ended up traveling roughly 10 additional astronomical units farther than Voyager 2 before finally reaching its own crossing point. A difference, the Iowa researchers concluded, meant the heliosheath. Now, the thick, turbulent transitional region just inside the Heliopause has a meaningfully varied thickness at different points around the heliosphere's surface, rather than forming a simple, uniform layer of consistent depth everywhere around the bubble. There's a specific engineering limitation baked into how Voyager 2's frequency detections actually work. And it's worth understanding honestly, because it shapes exactly what kind of data the spacecraft can still provide today. Voyager 1's plasma wave instrument retained a functioning wideband receiver capable of returning detailed, high-resolution spectra, even if only for brief intervals lasting a matter of seconds, gathered a few times each week, letting scientists sample a broad range of frequencies almost continuously over time. That capability is precisely what allowed Voyager 1's team to eventually detect a persistent, continuous plasma hum starting in 2017, a steady signal rather than the occasional dramatic bursts triggered only by major solar disturbances, essentially the difference between a weather station taking readings every few minutes versus one that can only report back whenever a storm happens to roll through. Voyager 2 never had that same advantage. Its wideband receiver stopped functioning at some point during its long journey, leaving the spacecraft dependent entirely on a lower resolution instrument called a spectrum analyzer, capable of detecting oscillations at only a fixed set of specific frequency channels rather than sampling continuously across the full spectrum, a coarser, more limited tool than the one still working on its twin. That's precisely why Voyager 2's frequency detections show up as distinct cataloged events in early 2019 and again on that specific date in mid-2020. Rather than as the same kind of ongoing, continuously monitored signal its twin has been able to track for years. Even working with that more limited instrument, Voyager 2's detections landed specifically within its 3.11 kilohertz channel, a testament to how precisely tuned even a stripped-down, decades-old piece of hardware still needed to be to catch a signal this faint at all, functioning reliably decades past any reasonable expectation for its working lifespan. Despite that limitation, the handful of distinct events Voyager 2 has managed to catch turned out to be scientifically valuable in their own right. Researchers studying both spacecrafts' combined data found that Voyager 2's occasional detections, spaced out across 2019 and 2020, provided evidence of what scientists call a radial gradient in the very local interstellar medium, meaning the density of the surrounding plasma doesn't stay perfectly constant with increasing distance from the Sun, but instead climbs. Gradually, as both spacecraft continue moving farther outward, each additional astronomical unit of travel corresponding to a small but measurable increase in the surrounding electron density. That gradient closely matched a similar pattern Voyager 1 had already documented independently, using its own considerably more frequent detections gathered across a much longer, more continuous stretch of data. Two spacecraft, carrying similar but not identical versions of the same instrument, sampling different points along the boundary at different times, arriving at a consistent picture of rising interstellar density, the farther out each one traveled, gave researchers real confidence that the trend wasn't a fluke specific to either spacecraft's individual location, but a genuine, large-scale feature of the surrounding interstellar medium itself, something shaping an entire region of the tide to wherever one particular spacecraft happened to be passing through at a given moment. That rising density trend has continued generating fresh data in the years since, adding new chapters to a story neither spacecraft's original engineers could have anticipated when Voyager first launched in 1977. Researchers tracking the plasma wave measurements from both spacecraft have noted that density readings taken well after each initial crossing continue showing higher values than what either spacecraft first measured immediately after reaching interstellar space, an ongoing climb that specialists studying the data are still working to fully explain. Some researchers have speculated the rising density could eventually level off or even reverse once whatever structure is driving the trend gets fully sampled by the spacecraft passing through it, though that remains, for now, an informed guess rather than a settled conclusion. Every additional frequency event Voyager 2 manages to catch, however occasional and however limited by its aging hardware, adds one more confirmed data point to that ongoing, still unresolved question. It's worth being honest about how narrow this specific window of opportunity actually is, because both spacecraft are working against a hard, physical deadline that has nothing to do with the science itself. Voyager 2 runs on a radioisotope thermoelectric generator, converting the steady decay of onboard plutonium into electricity, and that power supply has been fading gradually and permanently every single year since launch, losing a small, predictable fraction of its output annually, the way a battery slowly weakens even when it's never actively drained. Engineers have already had to power down instrument after instrument across both spacecraft simply to keep the remaining ones alive a little longer, carefully rationing every remaining watt of power between the handful of instruments still considered scientifically. Mission teams have said openly that within the next few years, the available power will finally drop below what even a single surviving instrument needs to keep functioning at all. That means every additional frequency event to Voyager 2's plasma wave instrument manages to catch, however rare and however limited compared to its twin's more capable equipment, represents data that will very likely never be collected again in most of our lifetimes, since no other spacecraft is currently positioned to reach a comparable distance with a working plasma wave instrument any time in the foreseeable future, let alone launched, traveled, and arrived there within a time frame most people reading this will personally live to see. There's also something worth sitting with in exactly how this specific kind of discovery gets made, because it's a genuinely unusual way for a scientific finding to unfold. Nobody built Voyager 2's plasma wave instrument with the expectation that it would still be operating, still catching faint, occasional frequency events, more than 4 decades after launch. From a region of space, its own designers had no reliable way to predict the properties of in advance. The instrument was simply built to be as capable and as durable as 1970s engineering allowed, pointed, outward, and left to keep transmitting whatever it happened to find for as long as it possibly could. Every frequency reading that's made it back to Earth since 2018 represents exactly that kind of quiet, unplanned bonus, data nobody specifically promised would exist, arriving anyway because an old machine kept working long after anyone had a right to expect it would. So here's where that leaves things today. Somewhere more than 12 billion miles from Earth, Voyager 2 continues moving outward through interstellar space, its aging plasma wave science instrument still capable. On the rare occasions, the surrounding plasma happens to oscillate at just the right moment of catching a specific measurable frequency, and relaying it back across a distance so vast that the signal takes over 18 hours just to arrive. That frequency isn't a message, and it was never meant to sound like one. It's a direct physical readout of the density of the actual space Voyager 2 is currently passing through, a genuine scientific fingerprint of a region of the galaxy no human instrument had ever sampled before either Voyager spacecraft got there. Think about what it actually took to arrive at a number as specific as 3.11 kilohertz, and what that number represents once you set it against the full sweep of the mission's history. A spacecraft launched in 1977, carrying instruments built with technology that predates the personal computer, traveled for more than 4 decades through the gravity of 4 giant planets, past the edge of everything the sun's influence can reach, into a region of space genuinely unlike anything its own builders had direct evidence of, and still returned a precise, usable measurement of that region's physical properties. Cross. checked against an independent measurement from its twin, sampling a completely different point along the same boundary. That kind of result doesn't happen by accident. It's the product of careful engineering, patient decades of operation, and researchers willing to keep watching a limited aging instrument closely enough to notice a single faint spike worth writing down. Every additional event still waiting to be caught, using hardware that has already vastly outlived every expectation placed on it back in 1977, adds one more confirmed number to an otherwise almost entirely unmapped stretch of the universe, quietly building, one faint kilohertz reading at a time, the only direct catalog of interstellar space that humanity has ever managed to compile firsthand. Whatever frequency Voyager 2 picks up next, whenever the surrounding plasma happens to oscillate loudly enough for its aging instrument to notice, will very likely be added to that same catalog in exactly the same quiet, unglamorous way this one was, not with an announcement claiming contact, with anything beyond our understanding, but with a careful, patient team of scientists, confirming, once again, exactly what kind of space their 48-year-old spacecraft happens to be sailing through today.